Saxon's Calculus Lesson 103 is about absolute value. So if I jump to example 1, where they give me y equals e to the absolute value of x, and they ask us to find dy over dx. So because this is an absolute value, I know I have both a positive solution and a negative solution. So for the positive solution, it's y equals e to the x for values that are positive, greater than 0. It is the negative value of, and we're just talking about where the absolute value is, so e to the negative x, when we have values that are less than 0, so we're in the negatives. Now, when you derive e to the x, you get e to the x. But when you derive this one, the negative one that is here that's coming down to the front makes it negative e to the negative x for not changing the derivative. And since these are two different answers, not the same matching answer, you do not have, it's not defined, is basically the answer. You can't do the derivative in example 1. Example 2. If f of x equals the cosine of the absolute value of 2x, find the derivative of x, of x. For a split second I thought it said plug in 2. All right, now we are going to again, split it into its positive and its negative format. Now, they suggest in example 2 that you graph each of these, and I was choosing not to. I was kind of doing it in my head. So cosine of 2x, when we are greater than or equal to 0, because we know that a cosine starts at an above spot, so there is an answer for the 0 there, so that's no problem. And then cosine of negative 2x for the opposite, when we are less than 0. So when I derive cosine of 2x, I get cosine goes to negative sine, so we get negative sine of 2x. The 2x gives me the extra 2 in front. Now what happens when I do cosine of negative 2x? Well, the cosine goes to the sine of 2x, and technically it should be negative 2x, but that negative comes out here to the front where there was already another negative which made it positive, but when I derived the negative 2x part, I went back to the negative 2. So again, if you want to write all of those negatives out to prove it to yourself, but basically since this is the same answer, not the problem we had up here, I could have chosen to box either one. I just boxed this bottom one, but this is the answer that we're getting for the derivative. Now, example 3. If f, just a second, where did my f of x go? No, that's example 2 again. Wait a second, let me flip the page. Much better, example 3. Okay, so we are integrating from, they give us negative 3 to 3 for the absolute value of x plus 1 dx. Now this one I did choose to do the graph because I need to see what is exactly happening so I know where my boundaries are. So when I do the positive version of x plus 1, I know that it's a v because it's in the absolute value. And normally the v would start at 0, 0, but this tells me that it's going, because it's the absolute value is acting as a parenthesis, the opposite, which is negative 1. So the v begins at negative 1. So then I just wrote this was the positive side, this was the negative side of the graph. And you can do other points to prove it to yourself, but this is where you get to. So now I know that when I am integrating the negative version, it's starting at negative 1 and then going to the lowest it could, which highest for this value is negative 3. So even though I didn't write that we were stopping at these places, we're stopping at those places. And then the dx plus the answer for the area under the curve on the positive side. So that one is going from negative 1 to the 3 with the x plus 1 version dx. And so then we just do the integration. So this becomes 1 plus 1 makes the 2, which is why it's x squared, and then it flips in front, so it's minus the 1/2 x squared. The 1 goes to minus x, and we are plugging in from the negative 1 to the negative 3, plus, and then I just had a minor boo-boo there. I was in this mode, I guess. When we integrate here, we get that same 1/2 x squared, it's just no longer negative, and then a plus x, and now we're plugging in from negative 1 to 3. So then I did the math calculations down here, but you're going to punch it on your calculator, plug in the negative 3, get an answer, plug in the negative 1, get an answer, subtract those two answers, and you come up with 2. Same thing here, plug in the 3, you'll get an answer. Plug in the -1, you'll get an answer. And subtraction of those ends up giving you 8. And so now you're dealing with a 2 area this side and 8 area this side. So the combination of them is, of course, 10. All right, example 4. Find from -pi/2 to 0, sine of the absolute value of 2x. So again, they graphed it, I did not. And we're going to do our positive version, sine of 2x when we are greater than or equal to 0, sine of the -2x when we're less than the 0. And then sine comes from negative cosine. The 2 needs the 1/2 to undo it. And then, of course, the 2x is carrying the same, and that is going from the -pi to the 0. So then over here was my jotting down of numbers, but you're going to do it on the calculator and find the answer from, and I can't remember, but again, you're going to test it on your calculator. Cosine of 0 times 2 is 0. And that should be 1, I believe. And then 1 times the -1/2 is -1/2. Then when you plug in -pi/2, and if you are doing it as pi/2, make sure you're in radian mode, not in degree mode. And then that's going to be 2 times that, which basically kills off the 2 and left the -pi, which was -180 degrees if you want to do it in degrees. Do cosine of that and then multiply that by the -1/2, and you're getting a +1/2. And then those two together made 0, so it was irrelevant. Now, if you're trying to follow in the book, they didn't even work that part out. They just ignored it, but I thought that was kind of confusing. Then here, you're doing the same thing, 0 to the -pi/2, and this time when you do that punching in on the calculator, you get an answer of 1. Now, example 5, find from -pi to pi the absolute value of the sine of x. Now, on this one, I did go ahead and do a graph just to sort of show you what was happening. On the next 3, it was kind of important. So when we graph sine, we're starting in the middle, and we're going our swoop here, and then technically we would keep going. However, I knew I was bounded between 180 and -180, so it was only 2 sections in the positives and 2 sections in the negative. So when I'm doing the curve, of course, that's the part that comes down here. Now, you've seen that I put an X out here. I've X'd that piece of the curve out. Because it's an absolute value, I can't have negative answers. So it's flipping that up to the top. So it's 2 humps basically sitting side by side. So now, if I find the area from 0 to pi and I double it, I have found the area under both curves, rather than trying to go from the -pi to the pi. So that's why graphing this one was important, because it helped me understand which boundary to use here. So I'm doubling from 0 to pi the sine of x dx. And that takes me to, oh, and this is why I don't have a negative version of it. I didn't need it. The doubling took care of that one, to make sure I said that. So sine goes to negative cosine from the 0 to pi. Again, plug it in on the calculator, get an answer. This should come out 2 times 2, giving you a whole answer of 4. Now, example 6 says, if f of x is the absolute value of the sine of x minus 3/4, find the maximum value for f. Okay, this one I struggled with because graphing the picture was just not easy. You need to picture your normal sine of x curve, which would start at 0 and then go up to the high point and back down, just like we did here. I didn't label 1 and -1, but I figured you knew the difference. We are shifting it to the 3/4, and I thought yes, I did label that. Okay, so I labeled it here, and because it was, here is the 3/4 line. This is now acting as my x-axis would have acted. That's why you see the dot here starting in the center for sine. All right, now, if you go up, what is a solid 1 from the -3/4, that negative is lost in there, from here, you are Adding 1. So that's going to take you to a high point of 1/4. If you minus 1 from the negative 3/4, that drops you down to negative 7/4 here. Okay, so then after I had a rough understanding of what the normal sine curve looked like, the absolute value part gets rid of any of the places where I would have a negative. Now here's where it got a little bit tricky when I was trying to draw it. It's not just negatives here below this negative 3/4, it's absolutely negatives below the 0 line. So this little hump is the only thing that's in the positives that should remain where it belonged. So this curve here needs to be flipping upward into the positives, and that's what I was trying to do here. And so where did it was at negative 7/4. So if I flip that up here, that takes it to the positive 7/4 as the high point. Now my spacing here is really bad. 1/4 and 7/4 are way too close together. And if you're looking at their actual graph, this one is way higher than this one. This one's a little itty bitty bump, and this is like way higher because the 7/4 should be more up here. I just didn't, obviously in pen, couldn't erase it to fix it. So if you want to see the actual picture of what it looks like, it's there on page 507. And then, of course, this swoop is doing the same thing from here down to here, and then technically all the way down to here. This is coming, it should be all the way up to the 7/4. I was a little shy there too. Like I said, I was having trouble graphing it. So it's bumping up here as a very large swoop technically. And then the itty bitty little hump, which would have existed on the next curve right here, is what this one would have been. Anyway, you kind of get the idea. So now the question said, what's the maximum value? Well, what's the highest place I can get to on this graph? Well, that would be the positive 7/4. So there we go. Now, I could have avoided graphing the whole thing if I just recognized that this was taking me to negative 3/4, the height was actually 1, and found the absolute value of that negative 7/4, which was the low point, would be my high point. Either way. Now, example 7. Given that f is a continuous function for all real numbers, and given that the maximum value of the f is 6, and the minimum value of that function is negative 12, which of the following must be true? So they didn't give me any of these graphs. I had to think my way through them. So I started with the fact that I have a maximum value of 6 and a minimum value of negative 12. So I could have something that is swooping approximately like so. That fits a max of 6 and a min of negative 12. So this could be a picture for the function. Then I know that in the A, B, and C, A is talking about the absolute value of this graph. Okay, so now I need to fix this graph. Anywhere I had a negative should now be a positive. So this is supposed to be this swoop here from the 0 up, and then this that was going down is supposed to now be swooping upward. So you get the idea. Now that's the absolute value. Then we also have in the statements, B gives me f of the absolute value of just the x. Okay, so that changed the picture as well, and that meant that this swoop was still the same, but this value here dropped below and then came up with the swoop and zeroed out here at this x-axis. Okay, so once I had those 3 graphs, then I looked at A, says the maximum value of the absolute value of f of x is 6. No, it's 12. B, the minimum value of f of the absolute value of x is 0. No, it's a negative. The maximum value of the absolute value of f of x is 12. Yep. So that's where I was getting the answer of C.